Google Maps. It gets you to and from places. It finds you a restaurant, does all that stuff. But those kinds of APIs can be used to tackle all kinds of interesting problems. Like for example, here, University of New Hampshire has put together a little Maps API demo that shows you the Boston approaches coming into the harbor, and there's acoustic buoys listening for whales. And anybody can go and log into this website, and they can see what's the status, or they can use an iPhone and hopefully soon an Android app that will let you go and see the status of the whales in the Boston approaches. So for large ships that are trying to not run over endangered right whales, it's a great little tool, and Google helps support things like that just as a part of our normal mission. And we have some technologies that you guys might not be thinking about in terms of Google. You're used to search and maps, but we have all kinds of cloud teams thinking about strange things like data sensors. And we actually have a whole data sensing group, and they work with devices that aren't typically ocean, but they're very similar to what you might use in the ocean. They have little microcontrollers and whatnot, and they record all kinds of different data. And they go out and then they start processing that data, and these kinds of tools could be really exciting for folks in the ocean community. Here you see noise in the Moscone Center in San Francisco. It's recording sound all throughout a building. There's a large bump up here from Billy Idol. He had a concert in the building. That was kind of loud. But this gives you a sense of being able to do this stuff without a large team. So the data sensing team is 3 people working on it in their 20% spare time to go collect a bunch of data and analyze it throughout an entire building. So that's the kind of thing we want to enable here at Google. Now to bring it back to what you guys are used to seeing, we've been talking about AIS quite a bit. Here's the small end of things. We have Little Toot in Santa Barbara. It blows bubbles out of its smokestack. I like to bring it down to a more reasonable scale than giant ships sometimes. But this stuff is becoming more ubiquitous. And if you've used Google Earth, you've probably seen demos like this. This is in Boston. This is what we can do with Google Earth. It's 50 or 100,000 points. It shows you the construction of a natural gas pipeline from an offshore terminal bringing gas into the Boston area. The ship tracks show you exactly where they dug out the trench and laid a pipeline in. Great tool. You can get a sense right of what's going on. Unfortunately, 50 or 100,000 points doesn't scale that well for a lot of our problems. So we've been looking at how do we push our tools to do more points. And here we were able to take 400 million points, decimate down to 1 million-ish points, and start giving you more of a global sense, be able to work with it in real time. And we want to do things like let you attack that data dynamically. So as you scroll around the screen, you should be able to do, say, like a histogram of all the vessel's speeds that are shown in this particular display. And as you move, you should be able to see that histogram change on the fly. You shouldn't have to wait for like 2 days while your laptop grinds away, gets hot, and then crashes, instead of getting your answer immediately. So this is the kinds of things we're pushing on. And I'd like to introduce Paul and Brendan, who have been pushing really hard on our teams to make their tools go much farther than they have in the past. And their demos have really been cutting edge in terms of showing what we can do here at Google. Oh yeah.
Yeah. So basically what we're going to do is we'll walk through a few things that we've been working on recently in terms of analyzing ship data. And full disclosure, neither Brendan and I actually work in oceanography, but we find the data actually very interesting because it's a very rich data set. It's temporal, so you can get like multiple years worth of data, even centuries worth of data. The data is actually fairly high resolution temporally. You can get actually samples from some ships every few minutes or so, and there's actually just a lot of, for any one point in time, there's so many, like quite a few ships in the sea. So we're looking at ways that we can actually take all this data, this massive amount of information that's available, and build visualizations that can help people understand kind of what's happening at a global level, and give them also the ability to kind of drill down and look at what's happening at the local level in terms of ship traffic globally. So the first thing that we wanted to do, we're kind of working on the hypothesis is that client-side rendering is actually much more powerful for this type of analysis than actually rendering data server-side and then sending that data to the client. So by client-side rendering, what we mean is we're taking the data, we're sending just raw data points to the browser, and then actually rendering them in the browser using WebGL, which is the same technology that a lot of online games are built. Do you know anything about kind of technology about WebGL? Or?
Sure. I mean, the main thing is what Paul said was just bring down all the data and then hardware is now at a point where it can actually display millions and millions of data points. And by bringing all the data down into the client, it lets you sit there and tweak things on the fly. You know, what Kurt was talking about earlier, no sitting off to a server to go crunch some numbers or run it on your local machine. You just sit there with a slider and you play with it. And then you start seeing things that you really had no idea was in the data. You had no idea to run a statistical test for because you didn't realize it was there. So here we have 10 million points.
Yeah, sure. So this is an example. So this is kind of the first stage of our analysis as to like what is the power of actually client-side rendering, or what can we do with client-side rendering. So really the first question we asked ourselves is how many points can we actually transport to the client and actually render at any one time. So this is about 10 million data points. So each data point is actually 2 floats, one for latitude, one for longitude. And we're actually doing dynamic. I mean, this is essentially being rendered at 60 frames per second in the browser, using a technology called Canvas Layer, which is one of our open source tools that we use for, or that we released for the Google Maps API. So really, the idea with this technique is that you know, we can. This demo doesn't necessarily show it because we don't have any sliders, or we're not actually analyzing the data, but we basically proved to ourselves that we can actually render 10 million points relatively directly on the client. I can't remember exactly like the span. I think this is at least 1 year's worth of data or something.
I think it's 6 months of data from SpaceQuest downsampled just a tiny bit.
And what we're doing in WebGL is we're essentially just taking these points, and as points stack themselves up, if you have 2 ship samples that are right on top of each other, we're just blending them to make them more yellow. So it's kind of this kind of heat-based data visualization. So the really interesting thing that we thought about this is it's a quick and easy way. I mean, we actually put this demo together in probably a couple of hours to show, like, you know, density of ship traffic client side. So we didn't have to go through any process of rendering this and tweaking the data to get it to look right on the browser. Really, the tweaking was, you know, kind of manipulating some of the WebGL rendering, which is a couple lines of code. So in addition to actually getting the raw points across, the next question we asked ourselves is, well, can we start analyzing this data using some of the data points that are also available in AIS? So this is actually taking the speed over ground, and we actually are categorizing it. So we've converted it into categorical variables. Or categorical, I think we have 5 bins. The brightest color, the yellow, is actually the fastest ships. So this type of visualization, again, so we're transporting 10 million data points to the browser, plus another field for the speed over ground for the ships. And we feel that, you know, this type of visualization allows you to kind of make a lot more inferences about global ship traffic. You can not only see, like, what are the fastest lanes. There's a few surprises in here that you see. Obviously, ships slow down quite a bit in the Panama Canal, but they speed up pretty quickly once they get out of the canal. The Amazon River, you can see that you know, ships actually go relatively fast in the Amazon River, which is something that I wouldn't have assumed, because most other internal waterways, you know, it appears that ships are actually quite slow in the low 5 percentile of global ship speed. So this is one thing that we just decided you know, we can do. So at this point we're sending 10 million coordinates plus for each coordinate sending also speed over ground and actually categorizing that in the client side. We did something very similar. So we just, instead of taking the speed over ground, we're now taking heading. So heading is actually, since it's 360 degrees, we can apply that to a color wheel. So this is actually color. It designates directionality. So here you can actually pretty easily see, like, what the major shipping lanes. You know, I'm guessing you know, purple is kind of in this display here. Purple is going northwest, where the green and orange is going southeast. So it's pretty clear to see directions of ships at a global level. When you actually zoom pretty far out, things kind of blend to white, so you can see kind of heavy traffic areas. But once you zoom in, you can actually start seeing the directionality pretty clearly. So this type of thing, so working with you know, heading or the heading or speed over ground, both of these types of visualizations, once we were able to get 10 million points to the client, doing these, you know, additional variables, you know, was just a matter of actually you know, making sure we had the information and then and then rendering it. So actually changing the rendering of this data is literally in WebGL, a couple lines of code to say like, if the data has this variable, I want to color it this specific way. So one of the things that we started to explore as well is we wanted to look at derived data. So derived data and actually ways to get to the browser even faster. Because actually this is all running locally. So actually the data looks like it shows up pretty quickly, but you can imagine 10 million points shipping from the server to the client could be really relatively slow. I'm guessing it's probably in the hundreds of megabytes. Actually 32 bytes times, or 32 bits times 2 times 10 million. Anyways, quite a bit of data. So we started looking at ways that we can segment the data to actually stream it to the client. So it's actually usable in low bandwidth situations. And also, like I said earlier, that we're looking at deriving data. So this is actually two different kind of steps in our analysis in one. So one, you can see that the data is available instantaneously. So we're actually streaming the data in, segment by segment. So it's essentially playing a video, but it's actually playing the video in one direction. So there isn't necessarily a rewrite right now. And that we show here is this is actually this is the change in heading of ships. So what we did server side is we calculated change in heading. So we have these AIS samples from ships. When we have two samples from the same ship that are contiguous time-based, we can just calculate the delta heading. And now you can see, this visualization compared to the prior visualizations is that, the major shipping lanes have pretty much disappeared, but now you actually see very clearly the where ships are essentially standing still. There are a few exceptions, and one thing that we haven't done with this is obviously you probably want to do change of heading over change of time because these samples might be pretty far apart in some situations. But this compared to the visualization where we're looking at like global ship traffic and direction, all the same ships are here. It's just that the ones that are going in the same direction are essentially invisible in this visualization. So at this point, we're streaming data in dynamically. So we're streaming essentially like you'd stream video to the client side. Brendan was showing, on the right-hand side, we can do things like, and these were just essentially simple controls, but you can grab these little sliders on the right-hand side to do things like change the intensity of the points, or actually change the size of the points as well. So essentially, we're just leveraging WebGL to say, like, I want to render this point or this ship point differently in the browser, since we're rendering it dynamically. So at this point, so this is literally like a couple days or a couple weeks of work, maybe a couple days or a couple hours a day. We got to the point where now that we have the data kind of segmented and we can like stream it to the browser, we started thinking about animating the data as well. So, and at this point we thought, well, 10 million points is interesting. What if we actually take it up a notch and maybe go with about 300 million points? Our goal is maybe 1 trillion points or something like that. We haven't gotten quite there yet, but what we're showing here is so we're actually at this point, since we have the data segmented, what we wanted to do is download a piece of data, render it, throw it away, download the next piece of data, render it, throw it away. So at this point we're animating it. We're to the point where it is video. We're dealing with the same concepts as before. So we have this categorical data. The blue dots are the floating buoys, and the orange ones are actually ships. So this is all in the ICOADS database. You can actually pretty quickly see in this data set some kind of discontinuity. Sometimes you'll actually see a buoy that's colored orange. But this is all based on kind of the same idea. We're rendering this in the browser, so this is all client side. We have categorical data that we're rendering. The data is segmented into parts, so we can actually stream it down to the browser quickly. Really a bunch of interesting stuff. We haven't, back again, neither of us are really oceanographers, so we can't really make too much sense of this data, but we continue to work with people like Kurt. Also the SkyTruth team. Paul Woods, he's actually doing a lot of this work kind of in parallel. Very similar technology, actually using the same technology, but taking a more scientific approach to analyzing the data as opposed to us that's looking at it as from an interesting data standpoint. So some stuff that we're actually adding to these types of visualizations, or we plan to add to these types of visualizations, is things like downsampling. So right now we're actually streaming the data as fast as you can get it from the client to the browser. But it's actually not time synchronized. So as you have more data, we actually have data. The AdCoads database has data all the way back to 1650, I believe. But if you so if the data is more sparse for a particular time segment, it's just going to stream. How do I phrase this? So it's essentially not synchronized to time. So as there's more data, the visualization slows down. So some things that we want to do is actually time synchronize. So this plays like a video at a constant time rate. Also, one way that we could do that is actually downsampling the data, because this is at one point we're showing about 600,000. Actually, this is about 200,000 points or ships simultaneously, or points simultaneously in the visualization.
You mean at any one
moment
on
frame.
screen?
Exactly. Yeah. And again, this is still, since we are using client-side technology, I think this is rendering approximately on a fairly modern laptop about 30 to 60 frames per second. But so time synchronizing is one thing we're working on. Downsampling, so that we can actually throw away data when we actually have a whole bunch of it, because some of this data is actually pretty much redundant. Tiling, obviously when you zoom in, we're actually still downloading the data for the entire globe. So ways that you can actually save bandwidth, I think is another thing that we'd like to look into. And another thing is dynamically changing parameters. So what we're doing now is we have two parameters, the coordinates and then the ship type. But what if you wanted to do this visualization, turn off ship type and turn on heading, colorized by heading? How can you do that dynamically and still download in real time, or essentially as fast as the browser can pull it off the server? So more work to come. Again, we're working with Paul Woods on SkyTruth and a lot of this, so they'll be able to see more of this hopefully. And again, most of this code is a public database, the IPOS data. So we'll actually be releasing most of these samples open source as well, that database. Some of the earlier stuff you saw was Space Quest data. We can't release the data, but the technology for rendering is all pretty much available. So I'll show you.
Sure. So the last step is just kind of, so if you zoom in here, you can definitely tell these are individual points, and so as a whole, they as we zoom out, they look like lines, but they're not. And so the last thing we want to show, this is an older visualization, but using the Space Quest data, is just taking the obvious step of taking that data and actually animating through it as actual ship tracks.
So kind of the idea was that with the prior visualizations were essentially just taking every point and plotting it. So if 2 points, 2 samples are for the same ship, you can't really see that in the visualization except by the fact that they're relatively in close proximity or maybe kind of following the same path across the map. So Brendan, the research that he was doing was actually drawing lines between the points so that you can
yeah, so we actually create geometry that follows that path, and then the benefit of that is that you can actually take, so with Space Quest, or with satellite-based AIS, you have the issue that you only get data when the satellite's actually overhead, and so you might not have any data between 2 points that might be quite a ways apart, and so when you actually create that geometry between there, you can actually interpolate, you can guess kind of what was going on between those 2 points, and so here we're just using it for a nice visual effect where it kind of fades out as the path goes into the past, but you can imagine any sort of value that the ship is measuring at that point could be interpreted across that path.
I guess the other big point about this is you're using cloud services.
Yeah, so I don't know if you want to talk more about that. But
I'll talk a little bit about cloud in a second.
Okay, yeah. So Kurt will talk about kind of the back end of where this data is coming from. That lets us kind of use the benefits of the cloud and the benefits of client side, where even for the GPUs of today, there's still too much data, and so we use the cloud to pick the data that we want quickly, and then the client to show within that data the patterns that we want to highlight. And then as always, I'll show my favorite animation around Iceland here. There we go. I don't actually know what they are, but
you don't know what it is.
I don't know if these are fishing vessels or what they're doing, but it's more interesting than the shipping traffic.
They're fishing vessels.
Yeah,
they're loitering in one place.
Right. Yeah, they do that up here too, and then on the up here. So, yes, that's all we have. You want?
Yep.
Yeah.
And by the way, those URLs don't actually work. Sorry, they're internal. So basically, behind the scenes here is a range of services at Google that are running in the cloud that help get to the client. Don't worry too much about the details of this. We have teams that can help you out through all these different things if you're interested in working with us on this. We have virtual machines that you can spin up, and they're really affordable ways to do supercomputing. As Michael talked about yesterday, and Rebecca hinted at, the cost of computing can be really low. If you have to buy everything yourself, maintain it all yourself, build a building for it, things like that, that gets expensive really quick. So the flexibility that we try to give people is, I think, the real power of what's going on here. You can fire up 10,000 machines, shut them down 10 minutes later, and you're good. You pay for 10 minutes, and that's all you need to do. So that's the kind of model where it's on demand, it's when you need it. When you don't need it, it's out of your life. If you're using cloud storage and you say, you know, I'm storing a petabyte of data, I really don't need it, delete, well, it's gone. If you're not paying for it anymore, it's not using any resources. With a place like Google, we swap something else in there, and we've got other things going on. We'll just fill that space up. It's not a big deal. And I think that flexibility is something that's exciting, because I've been a researcher before Google with my little laptop, and I've had laptops actually get so hot that they've killed the grease and the bearings of your hard drive, and it seizes up. It's just not a fun day. And when it comes to data, it can be really hard to work with this stuff. You spend months working, trying to find the data, you dig into it, you get a picture, you don't know what it is, you can't do anything with it, and at this point you're frustrated. We'd like to change that and make it really easy. So Rebecca mentioned Earth Engine. Here's just a quick example of sea surface temperature in Earth Engine. You can start building things like classifiers, pick out fronts, load up as much data as we can, and we can really attack these problems at whatever scale you're looking to do. You can load up bathymetry or whatever your data set is from whatever area you're interested in, and bring in and let go of the pieces that you want as you need them. Mix and match between teams. If one team's got data loaded up, they're willing to share it, and they're in the cloud, you're in the cloud, you can work together. And you have all this available in Maps, and I want to mention one last thing, is that you can actually do indoor street view of your ships and other facilities. And I highly encourage you to talk to a trusted photographer that Google certified and see if you can do your own ship or core locker or research facility, and let scientists from other institutions who collaborate with you see your facilities before they show up. I got onto the Tommy Thompson, a 300-foot ship, looking at a diagram of it once, and I couldn't find the bridge when I hear over the PA, you know, chief scientist of the bridge. I'm like, I know it's up. And, you know, half an hour later, the captain's like, where were you? Turns out I was like 30 feet away. So that kind of thing is all about enabling you as researchers, scientists, folks in government and business to be able to do more interesting things and to do less time on the grungy IT work. You shouldn't have to maintain a giant supercomputer center to do supercomputer work in today's age. So thank you guys, and feel free to talk to any of us afterwards. We're happy to answer any questions, or actually, more importantly, hear your suggestions and comments. Thank you all. Oh, great. Questions?
I have a question.
Michael.
No, the visualization of the ships at sea is so incredibly beautiful. It suggests a living world. Is there any way to have that as like a screensaver or some sort of art? A grown-up MDA awareness kind of tool?
You know, we've actually rendered it out to videos, so I mean that's one thing we might be looking to do.
I think it'd be great.
But yeah, I mean something real time would also be reasonable as well. I mean, that's kind of the power of kind of what we're looking at in terms of streaming the data. Is you can you only need to stream as much data as you need to actually render.
I mean, literally, maybe last year's ocean traffic as a kind of watery zeitgeist. Here's what the ships were doing last year or last month, or it'd be an interesting kind of video to get just for all the people in the maritime industry.
Well, if someone who spent too much time looking at the data, like for example, when a hurricane came into New Orleans, you could see all the ships run away.
Yeah.
And they wait till the very last second to come there. It's really kind of frightening when you see the eye come through and they're still hanging out right around the edges. These kinds of things jump right out, and it is really pretty.
I think it's beautiful. It'd be nice to have a, not a mensurable, useful image, but a lovable, beautiful image. That'd be fantastic.
In the back?
Have you done any visualization of storms? I mean, it sounds like you captured it somewhat with this other data about ships, but I mean, I'm curious to know it does some of that kind of graphing, but
we've mostly been focused on getting rid of clouds. So we've been thinking the other direction, trying to create the synthesis to the cloud-free view of the Earth. The data, you can do the exact opposite. You can use that algorithm and flip the sense of it, and we would love people to try stuff like that. That's exactly what the tools are there for you to take that idea and run with it.
We also started looking, part of the reason we looked at the ICRAS data is that it's specifically atmospheric and ocean data, not just ship positions.
right.
And so you don't have to derive a lot of that stuff. You can just look at wind direction and wind speed. And so we have started working with using the point sample data to kind of interpolate over the larger field. But some of it is you don't want to reinvent the wheel too much. A lot of that's already done. And so, in fact, that's the purpose of that data. And so we're looking at what are the interesting new things we can do as opposed to what a NOAA supercomputer is already doing somewhere.
Yeah, I just don't know that NOAA has this. I know that NOAA doesn't have as much computing time probably as they would like to do those kind of visualizations.
Right. Yeah, less the visualization, but they already grid the data.
Yeah.
Yeah.
So we encourage people to load that kind of data, the output of the supercomputer, onto our systems, and then try out visualizing it in various ways.
Have insurers used it? I mean, I would think that's another potential application is, both for the ship data and insurers, but also for storm surge, and then superimposing it with.
I wish I could answer that question, but one of our core principles at Google is protecting user privacy.
Right.
And if they don't want to tell us,
right.
we don't know. We know they're a paying customer and they're doing really great things in their minds. As Michael talked about, people are using it like crazy. What they're doing, it's protected, we can't tell.
Right. I'm just thinking that the community of city planners and people all along the coastline who are trying to figure out how to do that and don't have the resources of the insurance companies, but
Yep.
anyway.
I would suggest taking a look at our gallery. It's maps.google.com/gallery, and that's where people can share stuff. And the gallery is growing like crazy. It's been released, a month and a half ago, something like that. So it's still getting going, but we're getting a ton of people adding stuff. I just go in and search for ocean. I don't know why I do that. But just pick your favorite topic, see what kind of maps are in there, and come back and take a look and see what people are adding. And you might actually find new collaborators in that kind of set. Someone who's really good at visualizing the kind of data that you're interested in. That's our real hope, is to make those connections. So it's not just an endpoint, it's a starting point for you to go out and use it just like search to think about who you want to talk to in the world and who might have data that you need or visualization skills. In the back?
Sorry if I missed something, but are you able to create a platform that moves along with the ocean currents, the sea surface temperatures, and the other things, the species, the animals that move across the ocean? Because there's concern about trying to load up, say, NASA's recent salinity data for the Sargasso Sea. We'd like to be able to display it on a moving platform.
So the platform itself doesn't move, but you can, as you saw up here, you can change and mutate the data with time and create displays. So we try to create a fundamental platform that can support exactly that, but we're looking for people to step up and go for it. So we're looking for what tools are missing for you to create that full visualization. If you have some programmers who want to go for it, what's missing from our tool set that they need to mix and match it the way you guys want?
If you look at the examples of time lapse that we had seen Las Vegas Sprawl or something else like that, that's bringing in Landsat data to do that. And so you just bring in sea surface temperature or something else the same way, and then be able to animate it.
But the animals that move along with the sea surface temperatures, because I'm hearing various places
Oh, so
you have the sea turtles that move with the sea surface